Hi everyone. In the previous video on dimensions and units, we looked at how we can identify a base set of different kinds of physical quantities, and from these base quantities and combinations of these base quantities, we can describe pretty much any type of physical quantity that can be measured. In the metric SI system, we have these 7 base quantities: time, length, mass, electric current, thermodynamic temperature, the amount of a substance, and the luminous intensity. And each one of those has its own base SI unit, but we're really going to focus on the dimensions for this one. So I can take these 7 base quantities and combinations of these base quantities to construct pretty much any kind of physical quantity that we're ever going to encounter. So for example, speed would be a length divided by a time. That could be in meters per second, or miles per hour, or inches per day. It would have to be some kind of distance, some kind of length, divided by some kind of time. Or if I'm looking at the density of an object, that would be some kind of mass divided by a length cubed. Mass divided by volume. Volume would be length times a width times a height, but those are all length as the type of dimension. So it would be kilograms per cubic meter or grams per cubic centimeter. Things like that would be our dimensions for density. We also talked about how if we multiply or divide different quantities, the dimensions of those quantities are likewise multiplied or divided. In the example for speed, we again say speed is how my position is changing in a certain amount of time. So my change in position would be a length divided by a time. Again, that's going to be some kind of time. So again, it would be in either meters per second, miles per hour, some kind of length divided by some kind of time. We also said that if we were to add or subtract or compare any quantities, they must have the same dimensions. If I have 3 seconds plus 8 kilograms, I cannot add those two units together. It makes no sense to add those different quantities that have different dimensions associated with them. If I had 5 seconds plus 3 minutes, well, those are different units describing the same kind of quantity, the same dimension. They're both a time. So there I could do a unit conversion, but if it's not the same kind of dimension, we cannot add, subtract, or compare those quantities. It would be like me saying, my mass is 30 meters per second. It's just a nonsense statement. We can't really do that. But we can actually use this to our advantage. We can use this as a quite powerful tool, because suppose we have a physical system that's described by some set of physical parameters. I've got an object with a certain mass, and it has some other properties. And each one of those properties, each one of those parameters has certain dimensions. And we want to take that set of variables and relate it to some other property of the system. How is it going to be moving? Is it going to have some momentum or some energy, or is it going to apply some forces to an object? Well, any equation that we introduce that relates some of those variables that describe how I've set up my system to some other physical parameter, any equation that we introduce must have that balance of units. And that severely limits which kinds of combinations of those original quantities will actually produce the right combination of dimensions. We call this dimensional analysis. And again, the basic idea here is just saying, if I have 2 sets of quantities and I'm trying to equate those quantities, they must have the same dimensions. It's the same thing as saying, I can't say that, my mass is 20 meters. It just doesn't work if it's not the right kind of dimensions. So let's kind of talk about this just conceptually first, and then we'll do lots of concrete examples. Consider a physical system that depends on some set of physical variables. We could have an object that has a certain size, a certain mass, maybe it's in a fluid that has a certain density, a certain viscosity. Identify all the physical variables that are going to describe this particular system. we can try to identify characteristic scales of this quantity with some particular dimension. So characteristic lengths, or characteristic times, or characteristic energy levels, things like that. And we can identify these scales by looking at what combination of these original variables give the dimensions that we're trying to find this characteristic scale for. And these characteristic scales basically describe when significant changes will occur in some kind of physical system. That might seem a little bit fuzzy as far as a definition goes, but these characteristic scales are going to be just approximations of when we expect to see significant changes. For example, if I'm looking at characteristic time scales, maybe I'm looking at the formation of a galaxy. Well, the characteristic time scales for that kind of motion, how a galaxy is forming, is probably going to be on the order of hundreds of millions of years to billions of years. But if I'm looking at, let's say, some kind of nuclear reaction and how that nuclear reaction is taking place, there might be significant changes on a time scale of maybe just a few microseconds, or maybe even down to nanoseconds would be the characteristic time scale for that kind of motion. So this gives us just a very, very rough estimate of which kinds of scales should we be looking at when analyzing the motions of these kinds of systems. Again, these could be time scales, they could be distance scales, they could be energy scales. Any kind of physical quantity, we can look for ways to estimate when these characteristic scales come into play by looking at which combinations of the variables that describe my system will give me those appropriate dimensions. So we're just going to go through a whole bunch of different examples, and let's start by thinking about a guitar string. So let's say I have a guitar string, and I can pluck this string to get it to vibrate in different ways. So maybe it's going to vibrate up and down, get that guitar string to vibrate. We want to ask, what might the motion of this guitar string depend on? Well, we can talk about the length of this guitar string. So how long is this guitar string? Call that scripty L. We can talk about the density of that string. So I'm going to use this Greek letter mu to describe the linear density as how much mass is there in the string per unit length. How many kilograms per meter or grams per meter. Like, again, we're just looking at the dimensions, so we can list this as a mass divided by a length. Again, I'm using the square brackets to denote what the dimensions of that quantity are. The length is, again, just a length. And it might also be important as to what is the tension in this string. How tightly bound is that string? So that force of tension, we talked about this in the previous video. The units of force are mass times length divided by time squared. So mass times length divided by time squared. And suppose I want to look at this guitar string and identify what is the approximate frequency that this guitar string is going to vibrate at. Okay? Is it going to vibrate a couple times a second? Is it going to vibrate thousands of times a second? Is it going to vibrate, only a couple times every week? We want to try to find a way of identifying what is this characteristic frequency scale. And a frequency would be described as 1 over time. Usually when we're talking about frequencies, we talk about frequencies in units of hertz, and 1 hertz is 1 cycle per second. But again, this can be any this frequency can just be 1 over some unit of time. So to identify this scale, we want to look at what combination of these terms will just get me units of 1 over time. There are different kind of formal ways of doing this. We're not going to do the full make a dimensional matrix and do operations of that matrix. We're just going to kind of do these examples by inspection. So we're trying to get 1 over time. The only one of these quantities that involves time is force. So let's start with that one. We're just going to start with saying, if I have a force, the dimensions of that are going to be mass times length divided by time squared. Okay. Let's see if we can get rid of those dimensions of mass, because our final answer, we don't want it to have a mass in it. So if I divide by this linear density, well, those masses are going to cancel out. So let's look at the tension force divided by that linear density. So that's going to be, the units associated with that are going to be mass times length over time squared, divided by this linear density. Well, that would be multiplying by the reciprocal. So that would be length over mass. And when we combine those together, we get units of, the mass would cancel out, we get length squared over the period squared. Okay? So that tension divided by the linear density, that gives us length squared divided by time squared. Well, I can get rid of this length squared by dividing by the length of the string squared. So if I have F divided by the linear density times L squared, well, we said F over that linear density was L squared over the period squared, and now we're dividing by a length squared. Those lengths cancel out, and now we're left with just 1 over the period squared. But we don't want 1 over the period squared, we just want 1 over the period. So we can get rid of that square term by taking a square root of this. So if I take this and do the square root of the force divided by that linear density times the length squared, that will give me units of 1 over time. And those are the units that we want for frequency. Okay. We can actually tidy this up a little bit and say, well, if I'm taking the square root of L squared, the square root and the squared term on that L squared are just going to cancel out. So I get this as my frequency is related to the square root of the force, the square root of that tension force, divided by the length of the string and the square root of that linear density. Okay. Now, this allows us to get a general sense of what is this characteristic frequency scale. So if I know what the tension is, and I know what the length scale is, and I know what the linear density is, then I'm going to be able to identify approximately, to kind of like within an order of magnitude. You know, could be larger by a power 10, could be smaller by a power 10, but probably in that range, we can figure out what that frequency is related to. And if you actually go through the full equations for this, if you look up the fundamental vibrational frequency of a string with fixed ends, we get the same equation that we just derived, only there's an extra 1/2 term in here. The dimensional analysis can't give us these, you know, just numerical terms, like if it's a 1/2 or it's multiplied by pi or something like that. But we kind of got everything else in that equation just by looking at what are the units. How do we take these original quantities for this particular guitar string and look at what combinations of those quantities will give me back a frequency. We can also test this out. You know, now we have a testable prediction. We can set up different guitars and change the tension force. We can change the length of the string. We can change what kinds of strings we're using, switch them out for higher or lower density strings, and actually test this out to see if it gives us this particular dependence on how the tension, the length of the string, and the linear density will affect the frequency. And for any musicians out there, especially any guitar players, well, if I increase the tension in the string, that's going to increase the frequency. So that part of the equation seems to make sense. Again, we'd have to do more work and more tests to kind of verify that it depends on the square root of the tension, but at least we've got increasing the tension increases the frequency. If I were to increase the length of the string and make the denominator of this fraction larger, that would lower the frequency. If I shorten the string, if I'm playing a guitar and I hold down my finger on one of the frets, and I'm playing a shorter string, that corresponds to a higher frequency. So the flip side of this would be lower string length means higher frequency. For the linear density here, well, if you've ever played a bass guitar, you'll know that they have very, very thick, dense strings. So for a bass guitar, we have an increased density in those strings, and that will have the effect of lowering the frequency of the sound that that instrument plays. Again, the thing that I want to highlight here is this result that we found purely came from looking at what properties this string is going to have that might affect its vibrational frequency, and how do we combine those terms in a way that actually gets us a frequency. And again, for the full details, you have to go and test this more substantially. This is probably a testing physics experiment that I'm going to be doing at some point later on. But for now, let's move on to another case. Let's say I've got a small asteroid orbiting a star. Okay. And let's say the star has a mass of capital M. So let's say we've got this star. We've got some small object orbiting around it. And we can look at the mass of this star, the semi-major orbit, the semi-major axis of that orbit. So again, mass is going to be just a mass. That semi-major axis is going to be a length. And it's going to depend on gravity. And we talked about in that the dimensions and units video that gravitational constant has units of length cubed divided by mass times time squared. Okay. So what we want to do again in this is try to identify a characteristic scale. In this case, I want to find out what would be the orbital period for this motion. You know, approximately how long will it take to go through one of these full orbits? Well, we want to find a time, and the only thing that has time in it right now is this gravitational constant. But for that gravitational constant, time is in the denominator of that set of units. So instead of looking at g, let's look at 1 over g. So 1 over g has dimensions of time squared times mass divided by the length cubed. Okay. Well, let's get rid of the mass first. So if I want to cancel out this mass, I want to divide this by the other mass that I have, the star mass. So if I do 1 over g times m, then those masses cancel out, and I get t squared, time squared divided by length cubed. Well, the only other quantity that we have in here is the semi-major axis of that orbit. That's going to be a length. So let's multiply this by length cubed. So that semi-major axis cubed over g times m gives us units of time squared. So basically, this combination of units, this semi-major axis cubed divided by g times m, will be related to the period of the motion squared. Those quantities are proportional to each other. This is basically Newton's version of Kepler's third law. The only thing that's missing from here is that constant, that dimensionless numerical factor 4 times pi squared. Everything else is already accounted for. We have the t squared is related to a cubed divided by the gravitational constant times the mass of the star. Now you might ask, and rightly so, why didn't we include the mass of the asteroid? And we might need to in going into further analysis on this. But since we're saying that this star is the one that has by far the dominant mass, and this little mass out here would not be dominant, if I switched it out for the small mass, the mass of the little object, that would, if this mass is getting small enough, we're saying it's a very, very small object, this time scale would get ridiculously large. Okay? much, much longer than the time scale that we have already identified. So more stuff is going to be happening on this shorter time scale when we use the larger value of m, the mass of the star, than if we were to include the mass of that smaller object. Let's look at another case. This one's also going to involve astronomy. Let's say we've got a gas cloud in space is undergoing gravitational collapse. So maybe in the early formation of a star, maybe I have this gas cloud out here. And let's say that this gas cloud has a certain density. So our gas cloud has a certain density, which would be dimensions of mass divided by length cubed. Let's say there's an approximate radius of this cloud, which would be units of length. And again, we're going to be using gravity. We're assuming that this is collapsing just under gravity. There's no other forces or anything like that affecting this particular system. And that gravitational constant is length cubed divided by the mass, a mass times a time squared. I again want to find out what is the time scale for this gravitational collapse. If I have this cloud of dust and gas in space, is it going to collapse in days, in years, in millions of years, in microseconds? How do we get this general time scale for this gravitational collapse? Again, these are not going to be exact. These are just giving us very, very ballpark estimates, again, to within maybe an order of magnitude in most cases. So again, we want to find a time scale, and the only thing in here that involves time is this gravitational constant, and we probably want, again, 1 over that gravitational constant. So 1 over that gravitational constant will have dimensions of mass times time squared divided by length cubed. Okay. Let's try to get rid of that mass, and the only other thing that has mass in it is this density. So we've got mass over L cubed. I want to cancel that out by basically dividing by this density. So if I have 1 over g times that density of the cloud, the result that we're going to get from that is 1 over g was m times t squared over L cubed. And dividing by this density, that's going to give us L cubed over m. The m's cancel out, but also the L cubes cancel out, so we're already at time squared. And finishing this up, we find if I take the square root of 1 over g times the density of this cloud, that gives us our units of time. This will give us, again, our characteristic time scale for how long this cloud will take to collapse just under gravity. I should mention that when actual stars collapse, at some point in the collapsing process, all that material is going to be heating up. And then there's going to be an outward thermal pressure that's slowing down this gravitational collapse. So for this part, we are just talking about the part of the collapse where gravity is the dominant force. We're not worrying about the increase in temperature yet. But even just with this, we can do some interesting stuff in figuring out what does this imply about star formation. This is going to be a little bit of an astronomy aside, but I think it's an interesting application of this dimensional analysis. Let's say I've got this giant cloud of gas and dust in space, and we've got this kind of average density for the cloud, and this time scale is going to tell us how long does this thing take to collapse. Well, we might want to know, is this giant cloud of dust and gas in space, is this going to collapse into just one star? Or is it going to collapse into multiple stars? How does that actually happen? Well, if we have this cloud of dust and gas in space, it's probably not going to be perfectly uniform. There's probably going to be some little regions where the cloud is at a little bit of a higher density. So little higher density pockets. So higher density pockets. Well, if we look at this collapse timescale, if I have a region that is a slightly higher density, that's going to reduce the time that it takes this thing to collapse. So if I have one of these higher density regions, these, overdense regions, that's going to collapse faster than the cloud as a whole. So what happens is this giant cloud of dust and gas in space, as it's collapsing, the higher density regions are going to collapse a little bit faster than the rest of the cloud. So instead of making one star, we make an entire cluster of stars wherever there were these little higher density regions. Again, this is a very, very kind of first order approximation of what's happening. If you want to get into the details of, how much higher density does this need to reach before it starts to fracture off and start to collapse, this process is referred to as fracturing, when this giant molecular cloud is collapsing and some of those higher density regions are collapsing faster. This fracturing process depends on, what's going on with the temperature of these gas clouds. When does this fracturing stop? Do we just get, all sorts of super, super tiny stars? And you have to go into more detail to figure out how those effects are going to happen. If you're interested in looking up a little bit more on that, look up fracturing for star formation and look up the Jeans mass. That's another term that comes up when we're looking at this fracturing effect. But again, one of the points that I want to make for this video is that even with this, just looking at the units of these quantities, the dimensions of these quantities, we can start to figure out some of the physics that's going on under the hood, albeit in a very, very approximate way. And again, all of these, we should try to find ways of verifying and testing all of these combinations of units that I'm presenting here. Okay. What if we're looking at the Trinity explosion, or the explosion of some nuclear device? And suppose I want to approximate how much energy output there is in one of these explosions based on how large the shock front is, the radius of the shock front, at some time t, where the density of the surrounding air has some particular value. So how large is the shock front? So this is for the explosion. We've got the radius of the shock front, which is going to be a length. We've got the time after the explosion, assuming the explosion is very localized at the beginning. So that time is clearly going to be a time. And the density of the surrounding air is a mass divided by a length cubed. And we want to find the energy scale. What is the energy output of this explosion? So that energy output, the units for that should be mass times length squared divided by time squared. Okay? We talked about that again in the previous video. So again, the goal is to figure out, can I find some combination of these terms, the radius of the shock front, how much time has elapsed, and the density of the surrounding air, for basically figuring out how much air has it pushed out of the way during that time, to get these particular units of energy. Well, let's start by just looking at the mass, since there's a mass in this energy output that we need, and the only other place where mass shows up is in this density term. So if I start out with just that density, that's going to be mass over length cubed. Time only shows up in the energy output in the denominator and in this time value. So if I do density divided by time squared, that's going to give me mass over length cubed times time squared. So the time squared is in the denominator. And then we have to go from length cubed in the denominator to length squared in the numerator. Again, the only other term that we have left is the radius of the shock front. So this is the last term that we have. So the way that we're going to get that is by multiplying this by r to the power of 5. So if I do density times the radius of that shock front to the power of 5 over t squared. If I multiply this by 5 powers of length, we're going to cancel out these 3 powers of length in the denominator and get mass times length squared divided by time squared. So this combination of terms, the radius of that shock front to the power of 5 times the density of the air divided by the time squared, that should give us the approximate energy output. Again, these are very, very approximate values, so we might be off by an order of a few, either above or below. But let's try and put this to the test with some actual data from from images from the Trinity explosion. And just to kind of make the comparison, 1 kiloton of energy, nuclear weapons are often measured in energy outputs in kilotons. 1 kiloton is defined as around 4.18 times 10 to the 12 joules. Okay. Since we're going to be using these densities and radiuses and times in our standard metric unit, density in kilograms per cubic meter, distances in meters, times in seconds, this energy should be in joules, so we're going to convert that to kilotons. Well, let's look at some of the images from the Trinity explosion. Again, this was the first nuclear weapon test ever done. So again, I've put the images where I got these from, the time scales on here. The density of air at this location is approximately 1.1 kilograms per cubic meter. So during these calculations, let me move this down here. During these calculations, the density of air that we're going to be using is around 1.1 kilograms per cubic meter. So I've tried to use this scale to get an accurate reading of what is the radius of this explosion, and I can show how I got that. Basically on PowerPoint, I drew these 2 lines on here. This one for the scale has a length of 2.6 inches, and this one for the explosion itself is 5.53 inches. So if you take that 5.53 and divide by 2 to get the radius, and then divide that by the 2.6 inches for that scale, that's the distance in hundreds of meters. So I got 1.06, so that would be 106 meters for the radius of this explosion. So again, you can check this yourself. I've included the references on where I got these images from. You can kind of analyze this yourself. But let's see, with this radius and this pressure and this time scale, what do we get for the approximate energy output? And just for reference, the accepted value is between 18 kilotons of energy output and 22 kilotons of energy output. So let's see what we get from this particular estimate. So our density is 1.1 kilograms per cubic meter. That radius distance is 106 meters, and we're going to take that to the power of 5, and then divide by this time squared. So 0.016 seconds, that one's meters, that's seconds squared. And if I run through that calculation, so 1.1 times 106 to the power of 5, and then divide that by 0.016 squared, I get 5.75 times 10 to the 13. And that would be in joules of energy. If I then divide that by how many joules are in 1 kiloton, so divide that by 4.18 times 10 to the 12, I got 13.8 kilotons for the energy output, the estimated energy output based on this image. Now, again, all we've done is say the units that I'm comparing with this should give me units of energy. And again, this is an approximation. We would only want to trust this to maybe within an order of 10, but we definitely got within a factor of 10 of the actual value. But maybe that one was a fluke. Let's look at another image. So this is a few thousandths of a second later. And again, we can double check to make sure that I'm accurately reporting the radius of these. So this is the second image on here. Let's do the same kind of thing. So that line, our reference is 2.6 inches. This one is, for the diameter, is 6.73. We divide that by 2 to get the radius, and then divide that by 2.6. And that's how many hundreds of meters you'd have. I got 129 meters for that one. So again, we've got 129 meters for the radius of this explosion, and we've got a new time. So let's run these numbers again. So 1.1 kilograms per cubic meter times 129 meters, and take that to the power of 5, divided by 0.025 seconds, and we're going to square that. If I run through those numbers, so 1.1 times 129 to the power of 5, and then divide by 0.025 squared, I got 6.29 times 10 to the 13 joules. Again, if I divide by how many joules are in 1 kiloton, I got 15 kilotons. Again, pretty accurate, pretty good matchup between these values. And again, since we're taking the radius to the power of 5, even very, very small errors in our radius could throw off our numbers by quite a bit. So I'm actually kind of surprised at how closely these are matching so far. But let's do one more of these. So this was taking a little bit while later. This is I tried to identify the outer envelope of this explosion, but this one's becoming a little bit harder to read accurately. So again, this one might be a little bit less high confidence. But again, we've got 175 meters for that. Let's verify how I got that number. So this time, that size scale is 2.21. The diameter is 7.7, so 7.7 divided by 2 to get the radius, and then divide that by 2.21. Messed that one up. Let me try that one again. So 7.7 divided by 2, and then divide that result by 2.21. I got 1.74, so that would be hundreds of meters. So again, around 175 meters. Let's see how the numbers work out for this one. So we've got 1.1 kilograms per cubic meter. We've got a 175 meter radius. We are taking that to the power of 5. And then dividing by 0.062 seconds, and we square that. In this case, again, this one is the one that I'm expecting to have a little bit higher error, but let's see what we get. 2 seconds, and square that. I got 4.69, so basically 4.7 times 10 to the 13 joules. And again, if I divide that by 4.18 times 10 to the 12, that one gives me 11.2 kilotons of energy. So again, this same method, we're testing this under a number of different circumstances. This is not going to be a coincidence that these match up with each of these different moments during the explosion. We can get pretty good estimates on the general scale. Is this explosion going to be less than a kiloton of energy output? Hundreds of kilotons of energy output? No, it's going to be somewhere in a few tens of kilotons. So again, these kind of methods, this process of dimensional analysis can get us some pretty good estimates for some quantities that otherwise would be very, very difficult to calculate. But again, these are still just going to be estimates. They are not the full equations. The full equations would generally involve some other numerical term that doesn't have dimensions associated with it. So this dimensional analysis cannot figure out what those more accurate terms are going to be. Now, there's a more kind of formalized version of how to actually express this, and it's called the Buckingham Pi Theorem. Okay? And the theorem basically says Any equation describing a physical system involving n physical variables that together involve k of the base physical dimensions can be rewritten in terms of n minus k dimensionless parameters constructed from those original variables. So for example, if I have a distance L, so if I have some distance in units of length, and I have some time, dimensions of time, and I have some velocity, which would be a length divided by a time. So that's 3 parameters, and ultimately there are only 2 of those base physical dimensions. Just length and time. Velocity would be a combination of that length and time. Well, I can rearrange this in terms of a dimensionless variable. I can write velocity times time divided by distance, and that combination of terms will have no dimensions. This will just have basically dimensions of unity, no dimensions at all. And if these are the only terms that describe my physical system, any equation that we're solving for is going to have to be in terms of this particular quantity. The quick identification of this would be, well, if velocity times time divided by distance is equal to 1, then we can rearrange this and say velocity is distance over time. Now, identifying that this dimensionless quantity actually is equal to 1 or equal to 2 or 4 pi squared or some other dimensionless quantity, that we'd need to do more work to figure out. But again, we can narrow down how many options are available for the kinds of equations that could describe this system. Okay? And this actually has a number of benefits. Again, when expressed in dimensionless parameters, it shows the equations do not depend on how we specify those units. So if I have this equation where velocity times time divided by distance is equal to 1, it doesn't matter what units we've expressed that in. That combination of terms will be the kind of important physical part of that equation. And when we're looking at mathematical problems that involve lots of parameters, lots of terms that are interacting with each other in sometimes complicated ways, describing it in terms of these dimensionless parameters can often reduce how much is going on with those equations and reduce it down to its simplest possible form. Okay. This can also help us identify when certain terms are going to be important or not. The classic example of this is what's called a Reynolds number. This shows up in fluid flows, where let's say I have a fluid with a certain density in mass divided by length cubed, a dynamic viscosity, which we're not going to go into full details, but basically if I have some fluid, some sticky fluid that's placed between 2 plates, and I start pushing one of those plates to the side in such a way that it shears the entire fluid. So it's pushing that entire fluid and kind of dragging it along to the side. It's a measure of how much force does that take to get to move at a certain rate, depending on the height of that column, the surface area. Again, we're not going to go into full details on that for this video. Again, potentially a future video. But this dynamic viscosity has units of mass divided by length times time. And let's say that this fluid is flowing through or around some geometry with a characteristic length. Like, let's say I have a fluid that's flowing, but there is an obstruction in the way. Okay? And let's say that this obstruction has some characteristic length scale. So, and let's say this is also flowing at a flow speed of u, which would just be a length divided by a time. I want to know, well, how is this fluid going to interact with this particular obstruction that has this particular geometry? And the Reynolds number is given by the density of the object, the density of the fluid, times the flow speed times that characteristic length divided by that dynamic viscosity. And that particular combination of terms is dimensionless. Let's quickly verify this. So we're looking at density times the flow speed times the length divided by that dynamic viscosity. So density is mass over length cubed. The flow speed is length divided by time. We've also got that length. So I'm going to need to erase a little bit more on here. And that dynamic viscosity, we said that has units of mass divided by length times time. So we can cancel out that length, and two of those lengths. And then we get mass divided by length times time over mass divided by length times time. That is dimensionless. But this Reynolds number, what it describes is what kind of a flow is this particular fluid going to have. So for example, if this Reynolds number is very low, then viscous forces are going to dominate. If the flow is going very slowly and we have a very high viscosity, like a sticky fluid, we're going to get what's called a laminar flow, where that fluid is going to nicely kind of flow around that barrier. It's going to be a nice smooth flow. We're not going to get any turbulence showing up in here. We're going to get this nice laminar flow. Again, if that Reynolds number is low. Okay. If the Reynolds number is high, if it's not a very viscous fluid, so it has a low viscosity, and it's going at a high speed, well, that's when you're going to get, if I'm going to have this barrier, that's when you're going to get all these weird vortices starting to form around there, and you're going to get a turbulent flow. Okay. So again, this will have an effect on which terms in the fluid flow equations are going to become important. Is it just a nice laminar flow where everything is staying nice and smooth, or we're getting all these little eddies and vortices showing up in the fluid as that fluid goes past that particular barrier? This shows up in all sorts of kinds of fluid mechanics problems, and again, we can use these dimensionless parameters to start to get an idea on what's happening with some of the physics in these problems. So again, there's a lot more that we could go into, and if people are interested in some of the side topics that I've introduced, throw those into the comments, but we'll call that good for this video. In the next one, we're actually going to use some of these methods to actually and test out some of these methods looking at pendulums, and again find another way of measuring what is the value of G, this time using pendulums instead of the projectile motion, but that'll be for future videos. As always, thank you for your attention and have a good rest of your day.